Okay.
Eine Abteilung, das heißt
So, what we're going to do today is a topic that became very popular in the last few years. Entanglement, quantum entanglement. And specifically, we are going to do which was proposed in 1963 by a physicist named Bill, and was the first demonstration that there is something unique about nature that is captured only by quantum mechanics. Okay, so let me start with the simple premises of entanglement. Entanglement tells us that if I measure something here, I determine something that happens there. And I determine it instantaneous, and there could be in another galaxy. Doesn't matter. Nevertheless, the influence of my measurement here happens there in times that are shorter than the times that takes light to get there. And the first one who understood this property of quantum mechanics was, as usual, Einstein, and it's a famous EPR experiment. EPR. And it was described as a thought experiment to show that quantum mechanics makes no sense. That was the main lines that Einstein concerned himself in the later parts of his life. And the experiment was the following. Take a spin equal 0 system. Okay, two spin half particles that are in the s equal 0 state. Okay, what does the wave function look like? Well, we learned yesterday that it's in a singlet state, and therefore the state of the system, if we assume that it's in a singlet state, is simply okay. So we had two particles sitting here in a state s equals 0. We took one of them in the modern language, which is borrowed actually from communication. They like to use two experimentalists, Alice and Bob. And if Alice measured spin up, so we know that the wave function collapses on this part of the wave function. So we can be sure that Bob measured down. And if, let's say, Alice did it at some time t, and Bob did it at time t plus epsilon, prearranged, and each one of them wrote the result in her notebook. When they'll meet and compare notebooks, it always will be, if Bob measured up, Alice will measure down, and vice versa. Although the times that a signal of light takes to get between Alice and Bob, this time epsilon is larger than epsilon. So spooky action in the distance, and more or less that's what you get in popular media about what is entangled. Okay, and if you stop for a minute and think about it, this is totally non-convincing. Why? Simply, I can do this experiment classically. Let's say I take two particles, red and black. I mix them. I give you something like that, close your eyes, you're going to the end of the room. Black. You have red. I know it. I had spooky action in the distance. Well, no. Of course not. So, the experiment as I described here has something more. What is something more? The point is that before the measurement, unlike what I did here, the spin of the first and the second were both indeterminate, and only after the measurement I collapsed the wave function on one of these branches. Okay, but how do you prove it? Because I can tell a different story that still will be classical and will give me exactly the same result. The two particles, before they leave, each one writes in its notebook, I'll be up, the second one will be down. When I measured, I'll tell I'm up, the other one will look in its notebook and say I'm down. Finish. This is a cartoon description of hidden variables. Hidden variables says you perhaps don't know what is the result of the measurement. If you measure the spin here, 50% up, 50% down. But the particles between themselves, no, they determined while they were here who will be up and who will be down. And there's no way for me to refute that claim. So here comes in Bell. And Bell came up with a protocol that shows that no matter what table the particles will arrange between themselves, I can repeat this experiment many times and get a statistical result that cannot be explained within the assumption that we have a table of results classically written between those two particles. Okay, and then you have the question, And the experiment was performed, and the results correspond exactly to quantum mechanics, can't be explained by classical physics. So now we'll have some time. I'll discuss at the end what all kinds of schools of thought took out of this experiment. But first, let's describe the experiment. Okay, first of all, Bell came up with the idea you have to have here some randomness in measurement. What do I mean? If Alice and Bob, both of them measure always in the z direction, there will be no way to separate quantum results from predetermined classical results. It's quite understandable for a case that you are measuring each time in the same direction. They could come up with a table telling them, I'm up in this direction, you're down in this direction. But it's also not enough for both of them. Let's say Alice will measure in the z direction and Bob will measure in 45 degrees to that direction. Okay, still the two particles can write down a table for this case, and I couldn't separate classical result from quantum results. The key is Alice will randomly measure each time x and or z, and Bob will measure randomly two other directions. I'm taking this direction because the effect is maximum, but we could choose any two random directions that don't correspond to Alice measurement. And they'll sit and do the experiment. Each time Alice will throw a dice or whatever, choose a direction that she's going to measure in, write down the result. At the same time, Bob will throw a dice, decide which one of these two directions will be measured, writes down the result. You take the whole list of a lot of measurements, do statistics, and the statistics are large. You get a result, and I'll define what it is, which cannot be explained in any classical description of what's happening. Okay, so that's the Bell inequality. That's the Bell's experiment. Bell in '63 suggested it as a thought experiment, but in around 87, 88 was performed in optics, not on spin particles, but on photons with polarization. People who performed it got the Nobel Prize a few years. Was it a year ago? Not long ago.
Can I ask you a question?
Sure.
I don't understand how both Alice and Bob can randomly choose their spin. I mean, you have only one freedom, like degree of freedom.
The direction of measurement. If I'm sending you a electron, any spin half particle in the x that is polarized in the z direction. I'm allowed to measure it in the x direction, right?
So the direction isn't.
I'm determining the direction that I measure, right? So what will happen? You'll have to change this basis in the z direction to x direction. See what are the amplitudes of measuring the first spin in in the x direction. Square it, and you'll get the probability of measuring it as plus or minus x.
You can do that, but when Alice, let's say, does that, Bob must be.
No, so Bob has, before, if they were polarized in the z direction, they had s equals 0, and they started with the z direction. If Alice or Bob measure in x direction, they collapse the wave function to that direction, right? And that should determine what this guy measured. Exactly.
Oh, so you say one person at a time chooses, okay.
At the time they can choose ahead. They shouldn't. The experiment is performed always with someone is first, someone is second.
Okay.
The big problem in experiment you can see that you need some separation of times between them. So, yeah.
How do you say, like, you said that the measurement, that's what determines the different result. That's what proves the entanglement.
Well, we will define it mathematically exactly. I'm now doing only the general idea behind it.
Yeah, so over there, when you show it, that when you drew it, yeah, that means like.
I measure in 45 degrees to x.
Oh, okay, that's the measurement. That's not the actual spin.
If you want, in the language of optics, and where do I put my polarization filters? That's something that I determine.
Don't get some sort of dot product.
Exactly. We will do the mathematics.
So,
exactly.
How does it change anything?
Because I collapse the wave to a different wave. It's not anymore this guy, it's some other components.
Okay. Okay.
Measurement in quantum mechanics, whatever measurement means, changes reality, basically. Yeah. That's basically the difference between quantum mechanics and hidden variables.
Yeah.
Hidden variables tells you have a reality. It's so complicated, it depends on a lot of variables that you can't measure. The result, because of that, looks statistical.
Yeah.
But, well, it's not amazing. You learn classical statistical mechanics. You said each molecule there moves, but you still can say what is the pressure and what's the temperature. Although you don't know exactly for each molecule in this gas container what it's doing, what is its velocity, what its direction. Nevertheless, you can say what's the temperature, what's the pressure, what's the volume, all of that you know. So hidden variables basically tells you there's a lot of things under the hood hidden from you. At the end, if you come and ask a question, is it up or is it down, it will come out 50-50. And this experiment is supposed to convince you that no, you can't explain it in this way. Okay, let's see how it's done. So I have here two directions. I can be very general, A and B. Okay? And the first, Alice measures up and down along the direction A. Bob measures up and down along B. The only measurements, no matter in what direction you put it, is still only up and down. It's a spin half particle. If you decide to measure it along any direction, your result will be up or down. Okay, so basically, if they are doing n experiments, n measurements, there are 4 outcomes that can come out. Either both of them measured up in their direction. It's not necessarily the same direction. Okay? Measured 1,000 times, 200 times, both of them up, and so on and so forth. Let's define a correlation function. Here. Oh. Of course, it depends on the directions A and B that I choose. Okay, that's just a definition. What would be the result if both of them measure in the z direction? I will start with s equals 0 state.
Be like antilinear.
-1.
-1. Why? I never can measure in this for this wave function both of them up. I'm measuring at the same direction. I never can measure both of them down. Half of this time I'll measure down, up down. Second half I'll measure down up, and divided by the total number. Because all of them are this, it's just -1.
Why can't I measure both up or both down?
Because I started with a spin equals 0 and spin equals 0. A singlet state says one of the particles is up, in the z direction, the other one is down.
Is the probability of getting 2 up, 2 down, 1 up or 1 down for a system where you don't know the spin is like equal?
Well, For it depends on your, if you know nothing about it,
Yeah.
so it's equal.
Okay.
But if I'll tell you that it's in a singlet, it's already not exactly.
When we know that it's 0, then it's supposed to be half and half, or up, down, and down, up.
If we know that it's 0, the only way that I can get it is up, down, or down.
Yeah, I'm asking if the probability of getting up, down, or down, up, if it's equal.
Well, both of them are multiplied by square root of 1 over square root of 2. Squaring the amplitude, it's half, so it's half on this and half on this. If I have a spin equal 1, I have a mixture, just because one of the components is this guy with a minus, and there is correlation, and two of the components actually you never measure up and down. So it depends on your initial conditions, as everything in physics. Okay. So I'm keeping this guy just to remind me that, and along this whole lesson, this is my wave function. Okay. That's classical. It's not classical, it's after measurement. How do I calculate it out of quantum mechanics? As everything in life in quantum mechanics, any expectation value, I have to use operators. Okay, so how do I get a measurement of spin in some direction A? We wrote it for X, Y, Z. We never wrote it in general. Give me some direction A. But it's almost trivial. This is the operator for measuring the spin in any A direction. Dot product between A and the three components of X, Y, and Z. Good. What is written here? Bob measures psi. Sorry, Bob measures the spin of the state psi. And then Alice measures the result of the spin in her part of the experiment and just expectation value. That's exactly the correlation. Actually, if Alice measures before Bob, switch the order of the operators, and since they don't necessarily commute, it could make a difference who measures first. Okay, now let's calculate the probability from hidden values for such a measurement. That's called CSHC. These are the four guys. One of them, Shimon, is, I think he's still alive, from the Technion. Actually, EPR, the Arzer, Rosen was also a professor in the Technion. So for some reason, a lot of people from the Technion are involved in these early stages. Okay, so what do I mean by hidden variables? I mean that I have a probability Okay, what does it mean? I have a classical probability. Give me a direction A. I have here some hidden variable lambda. And that table will give me the probability of measuring up in direction A. Of course, I'll have also A of A prime lambda. We said that I have to have two settings with Alice. And I'll have two settings with Bob. Each of them giving a probability of measuring up in this direction. Okay? And what else I need? I need some probability for this hidden value. What does it mean really? Those guys take a whole table indexed by lambda, and each one writes in this table, well, if I will be measured for A, I'll give this value with some probability. If I'll be measured for A prime, I'll give an up probability with some other probability. Same for B, same for B prime. So I have here a whole book of probabilities that each particle carries in its pocket, gets to the point of measurement, it pulls out the table, checks, throws a dice, and gives a result. Okay, that's a classical description of a hidden variable. So, under these conditions, instead of doing this calculation, I should do the following calculation. C, that's quantum. Right? Basic statistics. I'm asking what's the probability of measuring this correlation. I check in my table the probability of measuring up or down. And it gets a result. Okay, this is the probability of measuring any one of these probabilities. Alice and Bob choose each time whether to work with A or A prime, with B and B prime. Here I just wrote it shorthanded with writing all the primes. That is all the correlation for all possible states that are measured. Okay? Okay, now we have to remember
Can I ask you a question?
sure.
How can both Alice and Bob choose the direction? I mean, if it's a random process, then it might not conserve like the total spin.
Alice and Bob are experimentalists sitting with their measurement device. They wake up in the morning, decide to put some angle or some other angle on their measuring device. Who will tell them not to do it?
Also, when we try to measure the total spin, we don't care about the direction. We only care about like the absolute value.
When you measure for a spin half particle, you get h bar over 2 and minus h bar over 2, no matter in what the crazy direction you chose your measuring device.
Okay.
One explanation of conserving hidden variables, even with the limits that I put here, is to say, oh, the experimentalist cannot choose any direction. Particles already determine for the experimentalist what they can and what they can't measure. Now, it's a solution. It preserves hidden variables, throws out free will, and what happens there? Instead of having a table only for the particles also determine a table for the experimentalist, what they can measure. It's an answer, to my taste, a horrible answer. It creates more problems than solving. It's easier to say, yes, quantum mechanics is correct, than not to say, well, you think you have free will to measure in what direction you want. No, the particles already determine between themselves what you will go to measure. You can't say it's wrong, because perhaps they keep a table of the whole universes to particles and determine everything. Doesn't sound very plausible. Doesn't explain anything else. Well, at the end of the day here, since we are doing spin halves and just to avoid sticking into it h bar over 2 and so on, A, B, for each value of lambda, what those particles are keeping in the table is just, at the end of the day, 1 or minus 1 with some probability. Because we know that measurement of a spin half particle will give me h bar or minus h bar. So these are the possible values. So let's look on Bob. Well, these are the 4 measurements that you can perform. Or 4 results that you can see. Okay. Let me see what are the possible results for B plus B prime and B minus B prime, which is equivalent here to these 45 degrees rotation. So, okay, I just wrote the results pulled out. And what do I know? A and A prime have are probabilities between this guy is either 0, 2, or minus 2. Same for this guy, right? So this thing has to be smaller or equal to 2. Right? Can do the game also here. Minus, plus, and in this case we'll have so any combinations that I put in 1 minus, I can show that the result has to be smaller than 2. Okay. Okay, so that's for classical. Quantum. So I'm calculating expectation value of AB. Okay, let's choose one of the settings that we chose ahead. So A was direction Z. Or explicitly, okay? I'm just doing the expectation value for when I choose A and B as Z and X plus Z. Okay. One thing in life is simple here. This operator is easy. Why? It's Hermitian, so I can use it to the left. And I'm already in this basis. So I have here the case where I measure up, so should have screened on me. Okay, if I measure up, so this guy is up, what happens to this guy? It's not there, I didn't measure up. Okay. One, one. I'm not seeing where I'm missing.
Isn't it like H bar 4
I measured H bar over 2, I had half, and I'm just continuing to write. I think, oh, the only thing here, I'm missing oh, no, yeah, I'm missing a closure because of this guy. Here it's, the only thing I said, if SZ works on up, it gives you up. If it works on down, gives you down. And so let's look what I have here. Sx that works on up or down in the z direction together will give you an expectation value of 0. So this guy won't contribute. This guy with this guy contributes. Another h bar over 2. So all in all, we have h bar over 8 square root of 2 square. And minus the same game so all together will be h bar you look worried.
S doesn't work on both, like eigenvectors.
Excuse me?
S Z of 2.
SZ of
You made
2
it work
works
on
on both of them, on up and down. But it leaves me in up and down, and if it leaves me here on down,
Yeah.
this will kill it. This is up and this is down. They're orthogonal.
Okay.
So only one of those components comes into the expectation value.
Why is x down 0?
S of x down is not 0. If you want to be precise, you should take it and you'll get part plus and you'll get half and minus half for the up and down. But together
okay.
they'll.
Okay.
So I skipped a step here, but as I said, it's clear that it can contribute. You want it as an exercise, go and write down the two components and see that it actually comes out zero. Now you go and do here's the contribution for all 4 terms. You'll get here a result of so if I take the whole combination here, so I'm taking this guy as the minus term, the calculations that we did before. I get here h bar over 4 times 4 over square root of 2. Just combine. This is equal which is larger than 2 h bar 4. Excuse me?
It's smaller.
It's larger. Thank you. In the classical calculation, when instead of writing h bar over 2, we wrote 1 in each place, we got 2. So now let's stick in the result. It's h over 2 squared. And we determined that it must be smaller or equal to 2. Here we got an expectation value that is much larger, 2 times square root 2. So if I go and do the measurement and get as an expectation value this value, no hidden variable theory can explain it. Excuse me?
Why? Isn't the point of the hidden variables to show that there's a different probability?
Well, on the deepest level of the mathematics, you're playing here with two types of mathematics. What is the difference between classical probability and quantum probability? Classical probability, you work with real numbers, right? So they always sum up to 1, and that puts some restrictions that we used in calculating the correlation classically. That was what enforced us to get a value that is equal or smaller than 2. We built a convoluted correlation function, but it's our prerogative to define our correlation as convoluted as we feel like. And we got it must be smaller than 2, just because all the combinations of A times B, we saw that if B and B prime sum up to 2 and minus 2, which we did by construction, we got there that it must be smaller than 2. Right? In quantum mechanics, all our game is done with amplitudes, probability amplitudes, and we square it at the end, right? I'll give you a trivial and probably doesn't hold everything, but it holds something. If I have probability, two numbers, 1 and 1, what is the largest number that I can get? 2, right? If I have amplitudes, so I take 1 plus 1 and then square it, so it can come out 4. So it's different mathematics which gives you different behavior. And if I strip the whole metaphysical structure around hidden variables and whatnot, the question is, does nature behave like probabilities or probability amplitudes? Which is in the root of the thing what quantum mechanics tells us. You have a wave function. The wave function is an amplitude. If you want to pull out probabilities, do all kinds of stuff with operators, and you'll get at the end a probability. But working with amplitudes is not equal to working with probabilities. You get a probability only in the end, meaning that you can get different results. And here is an example of a different result. A correlation that classically can't be larger than 2, but quantum mechanically is square root 2 times 2. So that's the Bell inequality. You go and do the experiment, or someone who knows to do experiment goes and does the experiment, does the experiment, and that's what you get. So nature is not described by hidden variables. So what do people do with it? Okay, the simplest answer is that I think most physicists will tell you. It's not amazing. We're working with quantum mechanics already for 80 years, or more, already 100 years. Works wonderful. Why are you surprised that that works and your strange hidden variable description of nature doesn't work? It doesn't work because it doesn't work, because it doesn't describe nature. Quantum mechanics describes nature. Other people will go and tell you something. Okay, it's only local hidden variables. if those two guys can communicate somehow faster than light, everything is okay. But why all relativity stands and only these two particles suddenly can communicate faster than light? No good explanation. The other thing that I told you is it's called superdeterminism. It's not only the particles define their situation, they define also the experimental decision of what experiments to do. And it's a whole field of philosophy of physics, philosophy of science that still arguments still today. Another very important result of these types of considerations is basically the whole business of quantum computing. All quantum computing is built on entangled states. Entangled means that if you measure one, you determine something about the others. The correlations are not classical. Now, I guess that all of you have heard in the popular media that a quantum computer is simply because you have all these combinations with all these amplitudes. They don't say, they say the bit can be in any state, but also a classical bit can be in any state. That's not explaining what. And it runs in parallel all these states. This is complete rubbish. That's not what a quantum computer does. Why? And I'll give you the simplest argument why this can. At the end of the day, you have all these amplitudes connected to all kinds of basis states of the quantum computer. Okay, a quantum computer will really be just a string of ups and downs. Okay, which are the qubits. But at the end of the day, what do you do with it? Like with any quantum system, make a measurement. So you take all these exponential number of components of the wave function, and we discussed previous lecture why when you go into many body you get exponential number, and you end up, you collapse it on one state. So you don't stay with an exponential number of states which represent an exponential number of parallel computers. It's completely wrong. You somehow have to write an algorithm that will cause the whole wave function to collapse on one result or another result with a probability 1 according to the functions that you want that your algorithm will make. And that's why programming quantum computers is such a nasty business. It's very hard to come out with a way to cause a wave function to have an amplitude 1 on some component if the result of the computation is something, and on another if it's something else. Usually at the end of a computation you have all different probabilities, and a computer that says, well, the result is yes or no, 50-50 is not a very useful device. If I'll have time at the end of this course, I will give an hour or so and demonstrate one of the few algorithms that work on a quantum computer. But we'll see how. Okay, I'll stop here. And next lecture we'll go back to the mathematics of spherical harmonics. The end of the previous lecture. Okay.